Alright, so Hess law problems. You have to write the net equation if it is given. Here it's given. Then you have to manipulate these two equations given to add up to give us this. And if we're going to multiply an equation, we have to multiply the enthalpy by the same factor. So right off the bat, this is a pretty easy question because let's go one by one. Let's look at reaction 1. The reactants are carbon monoxide and oxygen, and it produces CO2. Now we want to keep this. We don't want to flip anything here because CO2 is a product, which is what we want. In our finalized equation, we want 3 carbon dioxides. Here we only have 1. So what are we going to do? We're going to multiply this entire thing by 3, giving us 3 CO. 3 over 2 oxygen, and 3 carbon dioxide. And then you have to multiply this molar enthalpy right here by 3. Not molar enthalpy, this enthalpy right here by 3, which is going to give you 849. Negative 849 kilojoules. Okay, perfect. Let's look right here. So here, we're going to actually want to flip this because we want iron oxide. We want this in our reactants. So we're going to flip this, right? And that's going to give us FeO3 goes into 3 over 2 O2 plus 2Fe. And then with the enthalpy, we're going to multiply it by -1 because we flipped this entire equation. We had this become a reactant and these become products. So now we're going to flip that, giving us positive 822.3 kilojoules. Now let's see what we can do from here. Can we cancel out anything yet? Well, as we can see, this right here is a reactant in reaction 1. This right here is a product in reaction 2, and they have the same coefficient, which is good because if we cancel these out, we're left with no oxygen. So now I'm just gonna rid of this equation to make it a lot less confusing, because if you see a lot of things. So now we've canceled out oxygen, so let's look at everything behind these arrows, right? I've created a blue border so you can just see what's behind the arrows. We have 3 CO and 1 FeO3. Now if we refer back to our net equation, this is literally what we want. 3 CO and 1 FeO3. So now if we look at the product side, look at this, refer to this blue barrier right here, we have 3 CO2 in reaction 1 and 2 Fe in reaction 2. This is what we want. So now we've done it, so we can combine these equations, we can add up the products, so we're going to get 3 CO plus Fe2O3, because we've added the reactants from reaction 1 and reaction 2. Reaction 1, its only reactant that remained after oxygen's cancellation was CO. Reaction 2 after oxygen's cancellation was FeO3. So we've added these two substances to become our reactants. We do the same exact thing for the products. 3 CO2 plus 2 Fe. Now, if we're going to add these reactions, surely we also have to add the enthalpies. So I'm going to do negative 849 plus 822.3, and that's going to give us an enthalpy is going to be negative 26.7 kilojoules. This is what we want. Now, I might have went a little bit fast there, so I'll go slower for the next question. So incorporate the same exact strategy. Let's look at reaction 1. We have 2Al. This is amazing. We're not going to change anything here right now. because we have 2 aluminum on the reactant side. You refer to net equation, you have 2 aluminum. This is perfect. Let's look at reaction 3. Reaction 3 has chlorine in the reactants. So the thing is, this is good, but we need 3 chlorine. And in this reaction, we only have 1 chlorine. So what are we going to do to reaction 3? Say it with me. We're going to multiply by 3. So this is going to turn into negative 845 times 3. This is going to be negative 5535 kilojoules. And just add a 3 to everything. 3, 3, 6. Okay? There we go. So now what we have to do next is somehow, because all we want on this side is aluminum and chloride. 2 aluminums and 3 chlorides. But there's a lot of stuff we haven't canceled yet, but we're going to get to that, okay? Refer to this. We want 2 aluminum chloride 3s solid. Here we have aluminum chloride 3 solid, but as a reactant, and we only have 1 of it. So we're going to flip this. We've successfully flipped it, and we need 2 of these aluminum chloride solids. So 2, 2. What are we going to do to this? We've flipped the equation, and we have multiplied it by 2. So now we're going to multiply this by -1 and multiply it by 2. In other words, we're going to multiply this enthalpy by -2, which is going to give us positive 646 kJ. This is perfect. Final thing we're going to do, is look at reaction 2. We still have HCl as a reactant, and there's no way to cancel it fully yet, because even if we cancel this and that, we still have 5 HCl's on this side, because 6 HCl's cancels out 1 HCl, leaving us with 5 HCl's. But this works out perfectly, because here we have 6 HCl's, right? So, and here we have 6 aqueous HCl's. And in reaction 2, we have it, but as a product. So if we multiply this by 6, multiply this by 6, and then we got what we're going to get. We're going to get an enthalpy of -448.8. Everything works out perfectly. This is going to cancel this, because this is a reactant, this is a product. This is going to cancel out this. And then this cancels out that. And then this cancels out this. And let's look at the only things we haven't crossed off. 2Al, 3Cl, and 2AlCl. So now let's just begin writing 2AlS plus 3Cl2G 2AlCl3. And then let's just add up the enthalpies. So that's going to be -1049 plus -448.8 plus -5535 plus positive 646, which gives us an enthalpy of now here we're not given the net equation, so we have to find that out. Solid plus O2 gas is going to produce Ag2OS. Now balancing it, do you notice how there's no coefficient on the Ag2O in this question, which means this is 1 mole of Ag2O, right? We don't want to attach any number to this. We don't want to attach a single number to our product right here. We want to keep this at 1 mole. So that means, because of the fact that there is only one oxygen here, the coefficient here has to be 1 over 2. It might be a little bit weird, because normally when you have a fractional coefficient, you just multiply the entire thing so that it's a whole number. But here you're going to keep this as a fraction, because we don't want to do anything to this product. We don't want to do a single thing. Let's see. Which one has Ag2O as a reactant? Reaction 1. That is it. The only one that has Ag2O as a reactant. The first one, at least. So, what do you reckon we do here? Because Ag2O right here is a reactant. So we're going to flip the entire thing and multiply the enthalpy by -1. So, let's do that right now. And then our molar enthalpy here, our enthalpy here is going to be 324.7 kilojoules. Perfect. Now let's look at reaction 2. Perfect. We have Ag as a reactant, but we only have one Ag. So what are we going to do right here? We are simply just going to multiply the entire thing by 2. So now we have 2Ag plus Cl2 reacts into 2AgCl solid. And the enthalpy on that is going to be -127 times 2, which gives us an enthalpy of -254 kilojoules. Okay, things are working out. So I'm going to start canceling as we're doing this, so then it's very apparent what we need to do. So first of all, immediately we can notice that 2AgCl on the product side of reaction 2 and 2AgCl on the reactant side of reaction 1, they're going to cancel. And in case you don't get it, if you have a variable on two sides of an equation, they're just going to cancel each other out. It's the same principle here. Let's see, what else can cancel right now? It seems nothing else can cancel. Somehow we have to cancel chloride, because we don't really want chloride. Chloride is useless at the moment. Let's see, what reaction has chloride? Reaction 4 has chloride. Okay, let's work with reaction 4. It only has half a chloride, so what are we going to do to this reaction? We're going to multiply it by 2, and also, because chloride is a reactant, we have to multiply by -1 to flip it. So now we have 2HCl gas is Cl2 gas plus H2 gas. And then the enthalpy for this, you're going to do times -2, is going to be equal to 184.6. Alright? Because we flipped this equation to cancel out chloride, we have to multiply by -1. We have to multiply this number right here by -1, and then we have to multiply by 2 since we're multiplying the entire equation by 2. So now we can simply just boop, boop. Oh, and would you look at that? This also cancels the HCl in reaction 1. Okay, this is perfect. So now on our reactant side, create a massive barrier right here. Now on our reactant side, don't look past this red barrier, look at the reactants. We have 2Ag and H2O, and on the product side, we have H2 and Ag2O. So we somehow have to cancel out the hydrogen and the H2O, which shouldn't be too hard, because if you are seeing the fifth equation, we know what to do. Just take a look. This fifth equation has H2 as a reactant, which cancels out the H2 product. It also has H2 as a product, H2O as a product, which cancels out the H2O as a reactant. So let's just add this in simply. No, don't even think about it. And just keep the enthalpy the same. Now, we just cancel this. Let me just use a different color at least. Let's just cancel this, cancel this, cancel this, cancel this, and wow. Look at the only numbers that aren't crossed off. The only things that aren't crossed off. 2Ag, 1/2 O2, and then we're going to look right here, Ag2O. Perfect. So now we have everything we need to do. So now we can just write down our equation, 2Ag solid plus 1/2 O2. Sorry for not writing the suffixes, but they're given in the data, so I can just glance over that. It's not an issue. And then we can just add up the enthalpies together. It gives us a molar enthalpy of -30.6 kilojoules. By the way, yeah, sorry for forgetting the negative sign. Make sure to keep track of your integers during this entire process, or else it might all go wrong and it'll be a horrible, sad story.